Hi everyone, here we go. So now that we have Maxwell's equations in place, we can use them to develop perhaps one of the most important results from Maxwell's equations, how you generate a radio wave, electromagnetic wave. This lecture today is highly mathematical, and especially in the context of the current mode of learning, I'm going to try and emphasize the principles, the ideas, the pictorial details, not so much the mathematics. That's always been an issue here. So we'll do the reading quiz, but before I do the reading quiz, let me walk you through the lecture to tell you what I think is the most important part. I'm going to spend a lot of time talking about these two pictures here, okay, more than you think I would do, okay. I'm also going to spend a lot of time on the PHET simulation, and that's going to be a separate lecture, so that'll be lecture 25B. And what I'm going to do here then is lecture 25A. There'll be two videos in your Moodle section. I'm going to tell you how you launch a radio wave and why this picture here, which might look to be kind of mysterious, really shouldn't be that mysterious to you. I'll tell you how electrostatics and time-varying fields change this picture into this picture, which is you'll get a bubble of a radio wave coming out that way. Then we'll start with Maxwell's equations and go through some horrendous mathematics to get the speed of light in terms of the frequency and the wavelength. Talk about some symmetries. And I'm going to talk to you about the geometry of an EM wave. And if you get those ideas, especially this picture here, okay, then you would have learned a lot. Okay? All right. So first the reading quiz. Both of these questions have to do with the geometry of an electromagnetic wave, and here's that geometry. It's the one on the handout at the end. An EM wave has an electric field and a magnetic field which are at right angles to each other. The E field is this way, the B field is that way. There's a right angle between E and B, okay? And this E cross B points in a K direction. K is a wave vector which has the magnitude of which is 2 pi over the wavelength. So here's the K vector. Sometimes we use K, remember not to confuse this with little K hat, which is the unit vector in the y direction. This is the wave number. It's the inverse wave number. That electric field is perpendicular to the wave number, and also the B field is. So these are three mutually orthogonal directions. And the way I get the direction of this is I take the E cross B, and that points in the K direction. Okay, it's hard to do it on this piece of paper. So if I want to know the direction of K, E cross B points in the K direction. Okay, so that's the answer to number 1 and number 2. EM waves have E fields and B fields which are perpendicular to each other here. Okay, with respect to the direction of propagation, EM waves have E fields and B fields which are transverse. They are transverse to the direction of propagation. Remember in sound waves from Physics 111, if I had a wave going in this direction, if that was the propagation direction, if the disturbance was longitudinal like sound, that was a longitudinal wave. If I had a string propagation, that's a propagation that's transverse. So EM waves are transverse waves. Okay. I'm going to do these simulations after this lecture. That's a separate lecture. But here's the picture that tells you a lot about forget about the mathematics, which gets pretty messy to begin with right away. Here's how you start to generate an EM wave. This is statics, okay, and this is time-varying fields, okay. Here's what I do. I start with a battery, and I connect it to a wire going that way and a wire going that way. And I close the switch, okay? And the question is, what's the electric fields and what's the magnetic fields? Well, here's the E fields, and these are the E field lines here, these guys here, and these are the B fields going here. Those B fields are into the page over here and out of the page there. That looks mysterious? No. Look, here's the this configuration after I close the switch, okay? But let me start here. Instead of doing it that way, let me take this battery and connect it to a parallel plate that looks like that, okay, plus and minus. So you know what you get. You get electric fields that go from the plus plate to the minus plate, okay. That makes E fields that go that way, okay, DC. Except that instead of doing that, let me put this wire over here and this wire over here, and then let me start to expand that wire. So here's the battery. Let me get a darker pen. Where is my darker pen? I could never find my pens. Okay, here's a pen. Okay, here's my battery, plus and minus, and I'm going to take plus and minus here, and the wires there. That makes E fields that go like that. E fields that go like that, plus, 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 minus, 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 okay? But now let me start to bend that wire, okay? So if I bend that wire, here's the wire coming this way, and the wire coming that way from the battery, okay? And I'm going to bend this wire like that. This is still plus. I simply take the two plates and I start to spread them apart a little bit. Do you have a feeling for what that does? Here's what it does, minus, minus, minus. It takes the electric fields. This is a parallel plate, parallel plate. The electric field has to be leaving this plus charge, entering that one, and it has to be perpendicular there and there. So it makes the field lines curve like that. Okay. These field lines, which are straight down there, go like that. Okay. Keep doing that, expand it some more, and if you keep expanding that, then you get this wire here with the plus charge, and this wire down here minus, okay, or a plate. The E field goes from here to here and curves like that. So that gives you the shape of the electric field here. What about the B field? Okay. Well, when I close this switch, to get this charge, which wasn't on there before, current has to flow that way. That's a conventional current going that way. That means electrons go that way. That's a conventional current going that way. So these two plates have a total current going that way. That makes a B field that goes this way, into the page here, out of the page there. Okay, so that's where I start from here. But look what happens if instead of taking the DC battery, I take an AC signal generator here. I start with the positive polarity, just like this, BN, E fields going that way. But then periodically I change the wave, okay? As I do that, these waves here end up being negative down there. So in the middle of one cycle, after one cycle, I make a little bubble that spurts that way and starts going that way. And that's the radiation process, okay? All right. So, look, here are Maxwell's equations. We're going to solve Maxwell's equations for a vacuum. So I set Q equals 0, I set the current equal to 0. So I want a radio wave, a microwave, a short wave, whatever it is, doesn't matter what the frequency is. I have four equations: Gauss's law for electricity, Gauss's law for magnetism, Faraday's law, and the generalized Ampere's law. I imagine that I have a wave going like this. If I do that, then if I take one little piece of the wave, this piece here, and make it bigger over here, here's what I have. Suppose I have just a change in E in two places. I have a stronger E here than I have there. If I take a loop around here to calculate E dot dl, that E dot dl tells me that I have to have a magnetic flux perpendicular going through there. Okay. Do that integral, and after a bunch of horrendous mathematics, calculus, what I get is I get a solution for this thing that says if I do that, this wave has to move in the x direction. I'm just not going to go through all the details of that here, ladies and gentlemen. Read it in the book. So that's the story. And the story comes out that if I get a wave equation like this, I know exactly what the velocity has to be. The velocity has to be this number here, a real fundamental value. The velocity of propagation is 1 over mu naught epsilon 0, magnetic property, electric property. That number turns out to be exactly the speed of light, c. Okay. So the disturbance propagates at the speed of light. What can we say about these two things? Here are the intermediate equations that we got along the way. Okay. So if you look at these equations, if I swapped E and B, let E get replaced by B and B by E, I get the same form of the equations. Okay. What that tells you is that E and B have the same dependence on X and T, they just differ in magnitude. So here's this amazing thing, huh? You know what electric fields look like. You know what magnetic fields look like. For a static parallel plate, you get parallel electric fields. But for a straight wire, you get circular magnetic fields. Totally different. Put them together in a radio wave, and they have the same dependence. Okay? And if you're a physics major or a pre-engineer, there's only one of you out of the 36. For the remaining 35 of you, here's the picture I'd like you to walk away with. Okay? Here's everything you need to know about an EM wave. Okay? Here is E, which is perpendicular to B. Okay? E, which is perpendicular to K, and B, which is perpendicular to K. Here's the E field, which is sinusoidal like that. It goes in the vertical direction. The B field, in its perspective view, goes that way. When B is 0, E is 0. When E is maximum, B is maximum, and so on throughout here. Okay. The wavelength, lambda, gives me a wave number K, which looks like that. Okay. And E, B, and K are mutually orthogonal. Okay. Those are the radio parameters on the reading quiz before. We're going to call this number the wave vector, and that's going to be related to the Poynting vector, which is next lecture. So that's the story. Please look at the Colorado PHET things, which I referred to. You'll learn more about this picture here in that, and I'd rather have you spend time on that than reading through the calculus here. Hope you're doing okay. Please keep sending me those proposals for your final project. Hope you're safe. Hope you're doing well. Take care of yourself. Take care of your families. Adios, everybody.